Hello everyone, my name is Jun Zhang from Nanyang Technological University, Singapore. I'm going to present our work called LB-L2L-Calib2.0, a novel online extrinsic calibration method for multiple long baseline 3D LiDARs using objects. Here is the contents: introduction, related work, methodology, and experiments. The objective of this work is to do the extrinsic calibration among multiple 3D LiDARs in V2X, the vehicle to everything. The benefit is that after calibration, the multiple LiDAR can be fused, so that we can expand the FOV, field of view, and avoid blind spots. Here are mainly three challenges. First, long baseline, large viewpoint difference, and inconvenient to use the targets. For example, the 30-meter baseline, the 90-degree viewpoint difference, and busy highway. In our previous work, the 1.0 version, we used the sphere as a target for the calibration. The benefit is highly accurate, but we need to use the sphere in advance, so it's inconvenient, time-consuming, sometimes even inapplicable, such as the intersection or the busy highway. So in the 2.0 version, we observed that the bounding box or the objects is very good common feature, because the bounding box center is viewpoint invariant and the vehicles are easy to obtain in the traffic scenario. Moreover, we propose an exhaustive searching strategy to build the correspondence between the different LiDARs. Here shows the flowchart of the method. It mainly has three components: the feature extraction, the feature matching, and global refinement. The novelty mainly comes from here. We use the objects in the traffic for the calibration, the vehicles, and the 3D object bounding box center is viewpoint invariant feature. Also, we propose an exhaustive searching strategy to build the optimal correspondence between multiple long baseline 3D LiDARs. In this page, I will explain our important observation. The bounding box center is viewpoint invariant. As shown in this figure, there are two LiDARs with a 90-degree field of viewpoint difference. And here shows the point cloud and the detected object and the bounding box center, shown in red and green. And we use the ground truth transformation matrix to transform them together. Then, by zooming in this bounding box, we can see that the red and the green bounding box center is very close to each other. So we can conclude that the bounding box center is a viewpoint invariant feature, even though these two LiDARs has a baseline of 32 meters and viewpoint difference of 90 degrees. The second novelty is the exhaustive searching strategy. Given these two sets of bounding box centers, how to build the correct or optimal correspondence between these two bounding box centers, we propose this exhaustive searching strategy. It works like this. Firstly, in the first iteration, we select three pairs of bounding box centers. LiDAR 1 is shown in circle, LiDAR 2 is shown in star, and the selected three pairs is shown in three colors: blue, green, and yellow. Blue, green, and yellow. Then we transform them together as shown here. Then we will calculate the distance between the three pairs. If one pair the distance is larger than 1 meter, then the fatality is 0. Then the score will be 0. In the second iteration, we select another three pairs as shown here: blue, green, yellow, blue, green, and yellow. Transform them together, and we calculate the distance. We find all three pairs the distance is less than 1 meter, so the fatality is equals to 1. Then we will calculate the RMSE error between these three pairs. Then the value is sigma 2. Then we will calculate the score as shown here. If the RMSE is large, the score will be lower. If the RMSE is lower, the score will be higher. Then we continue this step until we find all the combinations. And finally, we will find the highest score, and that one is the best match. For the experiments, we perform the in 3 scenarios: the car park, the highway, and the intersection, with different configurations. Here shows the rotation and translation arrow. The left hand shows the ground truth of the 7 configurations, 7 datasets. The right one shows the rotation arrow and the translation arrow of ours compared with DGR, 3DM, and SAP. We can find that ours always achieves the lowest arrow. Next shows 3 quantitative experiments in the 3 scenarios. First is the intersection. One LiDAR is on the traffic light, the other one is on top of a car, so it's quite challenging. And here shows the point cloud and the detected bounding box of the 2 LiDARs, as shown in red and green. Here shows the registered point cloud with our estimated extrinsic parameter. It shows it's accurate. The second experiment is performed in the real car park, as shown LiDAR 1 and LiDAR 2, and the vehicles are used as features. And here shows the bounding box detected from LiDAR 1 and LiDAR 2. And here shows the registered point cloud. This is LiDAR 1, this is the LiDAR 2. We can see it's quite accurate. In the third experiment, it's more challenging because it's over a highway. The vehicles are moving with a high speed of 90 km/h without a stop. This is LiDAR 1, this is LiDAR 2. Here shows the bounding box from LiDAR 1, here shows LiDAR 2, here shows the registered point cloud. And this is a real video. Thank you, that's all for our presentation.